This movie or this video, we're going to be talking about finding, dealing with density functions. This is another application of integration, and we actually talked about this idea a little bit at the beginning of the quarter. In fact, I think we talked about this very same idea. So this function is the density function for the rainforest. So it gives you the number of trees per square mile based on x, which is the distance from the coast. So as you go in from the coast, the number of trees per square mile changes, and you can see this is a decreasing function. So as you're close to the ocean, the forest is very dense, or there's more trees per square mile. As you go inland, it becomes less dense, and it seems to be only dependent upon the number of miles from the coast. So our mission is to calculate the number of trees in the whole rainforest. So it's 120 miles by 40 miles. And we have to calculate the number of trees. So of course the number of trees would be, if the rainforest was the same density, so in other words, it was the same thickness throughout the thing, all we'd have to do is take the number of, or the density of the trees and multiply it by the square miles of the trees, because this is the number of trees per square mile. So if we multiply it by the number of square miles, we should get the total number of trees. The only problem is the density is changing as we go in. That's why we have to use integration. If we just said that if the density function was just, 300 all the time, right? That would mean there's 300 trees per square mile. We just take the total mileage, square mileage. We take 40 times 120 would give me the number of square miles, and we'd multiply that by 300, and that would give us the total number of trees. But since the density is changing, what we have to do is we're going to use integration. And remember, integration, one of the key concepts of integration is it adds a bunch of little things up. So what we needed to figure out is what is it that we're adding up. So to deal with our problem, we're going to add up a bunch of little strips of forest that are roughly the same density. And as the number of strips grows to infinity, they will be the same density, because the thickness gets down to nothing. And that's what integration does, right? So let's draw one example. So here's one example of a strip that should have roughly the same density, because it's that whole patch of forest is the same distance from the ocean, right? So we could figure out, if we take a bunch of these little strips that are spread out along here, right? Remember, this is like a Riemann sum. So, and we find that if we find the volume for each one of those, the number of trees for each one of those, add them all up, we should get the total number of trees. So that's exactly what we're going to do. So we're going to do an integral, and we're going to integrate on x. So this could be dx. So we're going to go from 0 to 40. Right? That makes sense. And what we're going to put in here is the number of trees per strip. Well, the number of trees per strip is going to be the density function times the area of the strip, or the square mileage of the strip. So we're going to definitely have the 300 here, e to the negative 0.04x. Then we got to multiply that by the square mileage of the strip. Well, the strip, in this case, is just 120 by a little change in x, right? 120 by, and that's where the dx comes in. Okay? So we got 120 times 300. Let's move that out. 120 times 300 is, so we got 36,000 times the integral from 0 to 40 of e to the negative 0.04x dx. And if we integrate that thing, we get 36,000 times e to the negative 0.04, but negative 0.04, but the derivative of that would kick out a extra negative 0.04, so we need to divide this by negative 0.04. And we're going to evaluate that from 0 to 4d. Okay? So then, let's take this 3600 0. Yeah. Divided by negative 0.04. And I get negative 9,000. Oh, 90,000 actually. Times e to the, now we put 40 in there, and that would be negative 0.04 times 40. That would be e to the negative, e to the negative 1.6, and that would be minus, so we plug a 0 in there, and that would be e to the 0, which is just 1. So then we take negative 90,000 times e to the negative 1.6, and then we add 90,000 to that, because negative 90,000 times negative 1 would be positive 90,000. And we get 71,829 trees. Now, just for kicks, what if the density would have been 300 for the whole thing? We would have went 300 times 120 times 40. We would have got we would have got 1,440,000 trees. Which is about double that. It's over double that. Okay, so there we go. There's one example of density.